So today's webinar is on the topic optimize fluid flow and thermal analysis using Altair Inspire CFD. So in the today's webinar, I will be covering these topics, the introduction to Inspire for fluids and how to set up a fluid flow simulation in the Inspire user interface, how to set up a conjugate heat transfer simulation in Inspire user interface, and then we'll have a question and answers in the end. So before jumping to the main topic, let me give a short introduction about Mason Labs. As Ramya already mentioned, we are the official channel partner for Altair technology. Altair has 150 plus products in their portfolio, and we have a team with 25 plus years of experience, and we are growing every day. So our team's expertise include data analytics, AI, and simulation. So before going to the Altair Inspire CFD, let me give a short introduction to the Altair CFD solutions, the various solvers that Altair has under the CFD banner. The first one is the AccuSolve, which is the general purpose CFD solver, which has wide range of capabilities to handle industrial applications, ranging from single phase, multi-phase flow simulations, heat transfer simulations, headlamp simulations, and many more. It is FEM-based solver. It is fast and robust. Next, we have the UltraFluidX, which is specifically built for the aerodynamic analysis of ground vehicles, for calculating the force measurements, lift, drag, and other force calculations can be easily done using the UltraFluidX. It is based on the LBM method. So it is just similar to the virtual wind tunnel. It is similar to the wind tunnel experiments that you carry out. So there are a number of validations wherein we have obtained close results with the wind tunnel test. Next, we have the NanoFluidX, which is SPH-based solver, which can be used for the water weighting simulations. As you can see in the image here, let me take a pointer. As you can see in the right side of the image, the water weighting simulations can be performed using the NanoFluidX solver. Then we have the flow simulator, which is the 1D simulation tool. Next, we have the SimLab ElectroFlow for electronic cooling performance. The ElectroFlow is widely used in the in the electronic industry. Apart from this, we have the flight stream, which is widely used in the aerospace industry for the performance of aero vehicles. Then we have the Altair Inspire, which is advanced version, which helps designers to simulate at very early stage, which I am going to cover in the today's webinar. So before jumping into this solver part, let me speak a bit on the pre-processing tools. This is Altair HMCFD, HyperMesh CFD, where the AccuSolve is integrated. AccuSolve is the background solver for the CFD analysis. So this is the one complete user interface wherein you will be performing the geometry cleanup, meshing, flow setup, and post-processing. Next, we have the SimLab, where the number of solvers are integrated, wherein you can couple one solver to the other solver. Like you can do the structural analysis and the flow analysis, CFD analysis, and you can also couple one solver with the other. For this, the SimLab user interface is widely used. Next, we have the Altair Inspire. As I mentioned, it is a designer-friendly tool wherein you can create number of designs. You can generate number of different designs and perform simulations within minutes here, and then make modifications in your design at the early stage. So yeah, this in detail, I will be covering the user interface, and I will be performing the live demonstration on two of the simulations, 2 CAD models. So let me give a short introduction to Inspire and Inspire CFD. So Altair Inspire, it helps the designer in product development lifecycle from concept to reality while reducing the product time to market. The designer can create n number of designs and modify the designs with ease, and it is capable of uh, it is capable of running the simulations within minutes and giving you the ideas at the preliminary stage, which is very important in any product life cycle, which reduces the time. So about Inspire Fluids, it is a it is the design exploration tool which is used to rapidly evaluate the characteristics of fluid and thermal systems. It provides upfront CFD capabilities for product design with simplified pre-processing and post-processing workflows. So in the pre-processing, you don't have to spend much time in the geometry cleanup. It is directly the CAD file is imported and then you are directly applying the boundary conditions on the CAD. You are not spending much time on the pre-processing and you don't have to generate mesh at all. So this is one of the beauty of the Inspire here. Without the generation of mesh, you are directly assigning the boundary conditions and then you are heading for the simulation run. And based on the simulation run, you are again making the changes in the CAD design and coming up with the best optimized design. So these are the some of the advantages of the Altair Inspire. Here, you can easily access the fluid and thermal behavior in early designs for faster and better product designs. You can compute the pressure drops and process efficiencies, temperature fields at various locations. You can identify the flow patterns, recirculation zones in your CAD at the early stage. And some of the Altair Inspire fluid advantages are it is fast, robust, and it is based on the CPU and GPU based solver technology. And just like the traditional FEA based solvers, you don't need expertise in the simulation domain to carry out the simulation. It is friendly for the beginners as well. So this is how the user interface looks like. In the right side of the slide, you can see the Altair Inspire user interface. Here, the model is brought in. All the parts that are associated with the model are displayed in the model browser here. Then we have the property browser. Then we have the construction history, which I will be speaking in detail with the live user interface. So here there are various ribbons which are respect to the structure, motions, fluids, and design explorer and manufacturing, and print 3D for additive manufacturing. So here today's webinar, I will be focusing on the fluids part, wherein the flow simulations and thermal simulations can be simulated at very fast, at lightning speed, you can say. So these are the various options are available under the fluids, which are helpful for any kind of flow simulations. Yeah, these are about the various boundary conditions which are available as part of the Inspire CFD. So it is the embedded computational fluid dynamics solver which is embedded into the Altair Inspire CFD, which is doing the analysis in the background. So the various boundary conditions that are available are the inlet condition and the outlet, which is the pressure. Then we have the far field, and then we have the phase for assigning the temperatures on the part. Then we have the part if there is any heat source to be included in the simulation, we can assign the heat source considering the part as the boundary condition. Then we have the run section wherein you are running the simulation quickly and you are doing the post processing. So this all is done in a single user interface in the single ribbon here under the fluids banner. So now let me move to the user interface and do a fluid flow simulation. So the problem definition here is we have a wall wherein my intention is to study the flow pattern inside this wall. And then I'm going to rotate it in the next simulation. I'm going to rotate it a bit by some angle and then see the how flow distribution is. So in the first year, this is CAD, which is imported. In the second section, you are directly assigning which is the bounding solid here, and you are directly capturing the fluid domain. And in the third, you are assigning the boundary conditions directly, inlet and outlet uh, to the uh, to the inlet and outlet faces to the surfaces in the CAD directly. And in the fourth stage, you are directly running the simulation and you have the results with you. And if you feel like modifying the design, you are coming back to the any stage and making the changes and then rerunning the simulation. So this is the added advantage of using the Altair Inspire CFD over the other traditional solvers. By doing this, a designer can create n number of design and come up with the best optimized design. Yeah, let me go to the user interface and do this simulation. So I'm using the Altair Inspire 2025 for the today's webinar. Let me open it. Okay. So this application is open. So let me give a short description about the user interface and then move ahead with the simulation here. So I'm currently in the fluid spanner here. So in my left side of my slide, I have the model browser. Currently it is blank, no parts, no solids, no CAD is imported. Then I have something called construction history. If you're not able to see these, you can activate anytime from this view section. Currently, the model browser is on. You can activate the property editor, wherein you will be able to see the various boundary conditions assigned. The properties with respect to that will be displayed here. And then you have the construction history. So yeah, I will speak more about this part in the simulation. Next. Yeah, that is all what I need for the today's simulation. Let me import a CAD now in the desktop. Okay, so this is the basic flow simulation which I'm going to perform. So I have just imported a CAD. So whatever you do in this modeling browser, that will be recorded in the construction history. So now you can see I have imported a CAD import. It is recorded here. So now let me uh, auto color for better visualization. So let me show you what all parts it has. In the model browser, you can see there is a left solid, then there is a right solid, then there is a handlebar here. So we have three parts in this CAD. So this is how it looks like. The flow passes from here and it exits from this location. So this is the basic flow setup. In the next simulations, what I'm going to do is I'm going to give some angle to this and make a different fluid cavity. Let me show you by moving it now. Yeah, if I rotate it by some 15 degrees, the fluid cavity changes. Yeah, you can see the fluid cavity is different. So these kind of simulations wherein you are performing number of simulations, the Inspire CFD helps a lot. Let me undo it. To do undo, you just have to move this to the top. So that is what the beauty of construction history is. Now I am in my previous stage. The wall is not rotated. So here I have three solids. Now what I'm going to do is I'm going to assign the materials. Assigning material is very fast. Yeah, currently it is steel here. Now I'm going to assign the bounding solid. In the bounding solid, what it means is it tells the software about the solid that is in touch with the fluid cavity. So I'm going to select all these three parts here and I'm going to assign material to this. You can create any material that will appear here. For today's webinar, I'm going to select this aluminum as the material for this bounding solid. Then right click and say OK for this. Now, just look at this step now, how fast the fluid cavity extraction is. I'm just clicking on this and it automatically captures the fluid cavity inside the bonding body. So this is my cavity for this simulation, current simulation. I'm going to assign water as the fluid medium for this and say OK. Now I have bounding body as well as fluid. To show you the fluid cavity, let me isolate this. This is my fluid cavity here, and this is my bounding body. This is the outer solids. So show all parts. Now I'm simply directly going to assign the inlet condition here. This is my inlet. I'm going to give the average velocity. There are a number of options here: stagnation pressure, volumetric flow rate, velocity. I am going to use the average velocity here. Then, yeah, 1 meter per second is fine. Then the temperature 298 as it is. Say OK. Next, I'm going to assign the outlet here, which is uh, 0, which is atmospheric pressure here. Say OK here. Next, yeah, that's it. I'm just going to hit run button and then I'm going to have the results for this simulation. Before that, let me save this file. Save as. File name as all save. Okay, the file is saved. Before running, in the run, you have various options. So here I'm going to say, yeah, resolution. Here you can increase. Currently it is 0.5 mm here. Just see what is actually happening. If I increase the resolution to the high, you can see the number of voxels is increasing and the voxel size is reducing. And here you can see the grid size here, how it is varying. So currently I'm going to keep, yeah, 0.5 mm here. And then you can also use the symmetry if you want to. Currently I'm not using that. Next, in the advanced, the termination criteria, you have various options here, physics and equations, or physics, or only equations. I am going to keep physics and equations as the termination criteria for the convergence. Output frequency steps. So I'm going to keep it 200 here and maximum time step as 2000. And then if you have any surfaces where you want to measure quantities, you can add surface monitors here. In the current flow type, I'm going to use the turbulent. And this is the GPU, which is automatically detected. And if you want to validate, you can validate. You can hit on the validate and check. The message displayed here is your GPU is valid to run the fluid simulations. So it is CPU as well as GPU based solver. I'm going to check this on to improve the convergence. Now let me save this file again and now directly run. Directly click on run. So just see how fast the simulation is done here. So now here in the convergence plot, I'm going to change it to the numerical convergence and number of iterations here. 600, currently it is 700 iteration. You can see how the convergence is dropping. And if you want to see the engineering quantities, you can see how the average pressure and velocity is changing over the number of iterations. The simulation is complete. So let me click on this and say view now. So this is the post-processing window wherein the fluid cavity is highlighted and the pressure on fluid cavity is plotted automatically. If I want to see the velocity, I'm going to change it to velocity here. And let me take a cross section. Yeah. Let me take a slice plane. Okay. So here is the slice plane cross section wherein the velocity counter is plotted. You can see the legend here, how the velocity is varying from 0 to 3 meter per second. And next, if you want to simulate, if you want to see the streamline animation, I'm going to switch it off, section cut, go to the streamline, and here, let me increase the speed. So you can see how the flow is flowing inside the wall here. The streamlines are properly plotted. If I increase the speed, this is how the flow simulation is. So this is useful for the designers at the early stage where they can perform this very quickly and understand the flow pattern and flow characteristics inside their CAD model. And at any point, they can go back to their design and make changes in the design very quickly and come up with the better design. So if I want to plot the vectors here, so this is how the vector plot is. This is at the inlet and then at the outlet here. So now if I want to do the analysis for different angles, so I'm just going back to my CAD here. As I said, this is the construction history. I can move this line to anywhere. No, so now I want to move one step behind. So I have created a fluid. I'm moving it one step behind creation of fluid. So here, fluid cavity is not extracted. Now I'm going to move this wall by some angle. Click on this, give some angle. I'm going to give 15 degrees as angle. Say OK. Now I'm going to move this cursor to the previous stage, that is create fluid. So it automatically captures the fluid. So now see if I isolate the fluid here, look at the fluid cavity, how automatically it is extracted. So now show all parts. I'm going to directly click on the run button again here. So I have results for another design now. So this way you can perform number of simulations for number of designs within minutes and come with the better design. Numerical convergence. If you want to see the engineering quantities, you can turn it on. And if you click here, you will get Euris pressure, velocity, mass flow rate, volumetric flow rate, uniformity velocity at inlet and outlet, if you switch it on. So the simulation is completed for second design also. It hardly took around a minute. So let me open this now. See, this is the pressure counter. Next, I have the velocity. If I want to see the minimum and maximum, it will automatically display at which location there is a minimum velocity and maximum velocity. If I want to check the flow streamlines, I can see that as well. See how the flow pattern is. If I want to check the vector plot, this is the vector. So now you may see at the outlet, some of the vectors are reversed. That means there is some back pressure here. So if you want to modify the design, yeah, you can do that very quickly. Let me do it. So one method to eliminate the back pressure is to have some extended outlet. So if I want to do that, I can quickly extend this outlet surface to some distance. For that, I am again going one step behind, that is create fluids. Now go to the geometry here, extrude. In the solids, I'm going to click on this solid and extrude by some distance. Then I'm going to say it has combined with the previous solid and say OK. So this is how the outlet section is modified. And I'm going to move this cursor to the next stage wherein fluid cavity will be automatically extracted. Now you can see in the fluids, there is one fluid cavity which is automatically modified according to the design. So this I am going to run it again, show all parts, and directly click on the run. So it quickly performs the simulation and gives you the results within minutes again. So likewise, a design engineer can make modifications to his CAD any number of time using the Inspire CFD. Create as many as you want, as many as designs you want, perform the simulations, and make modifications to your CAD and come up with the best possible design for your product. So the simulation is complete for this as well. So let me see the results. View now. Here you can see if I plot the pressure here, this is the pressure plot. If I plot the velocity and see the streamline flow, so this is how the flow pattern is for the extended outlet. I'm playing it again with less speed. Yeah. So this is how the flow pattern is inside the wall for the modified design. So this way you can set up the fluid flow simulation in Inspire CFD. So let me close this demo one and move ahead with my next demo, that is conjugate heat transfer analysis. Let me go to my PPT. In my second demonstration, I'm going to perform this heat transfer simulation analysis. So here, let me give a description about the problem definition here. The first, we have a casing wherein I have the capacitor, I have some of the heat sources, and you want to see the temperature distribution inside this fluid, inside this domain. So what a design engineer can do is perform a basic set up a heat transfer analysis and perform a simulation, and then understand how the temperature distribution is. And if he feels like the capacitor position inside the domain is not at right place, he can he can make modifications to the design and keep this capacitor at different places and then perform the simulation again. So with that, the Inspire CFD helps designer to place these critical components at a perfect place. So this is what the advantage of Inspire CFD is. So let me do this demonstration. I'm going to the Inspire CFD, take a new, don't save. Let me import a CAD. Okay. PhD demo model. So I have a CAD file here. Let me close this property editor, which is not required to me currently. So in the model browser, you can see there are number of solids. That is part 8, part 7, part 3. Let me hide and show you what all part it has. Okay, show all parts. So if I hide this, I have a capacitor here. I have some parts here. Let me change the color, auto color, so that you will understand. So this is the side one, side solids. This is the base, and this is the capacitor. And these are some of the heat producing elements. So I want to see how the temperature distribution is inside this. So you can see this opening. Through this opening, the air flows in, and through this opening, the air flows out. So let me do this simulation quickly. So here, what I'm going to do is at my first stage, okay, there is something called embedded solid here. Let me explain what it is. Say you have this capacitor. and you have no idea whether it is placed at a perfect place or not. So you treat this solid as the embedded solid, because after a simulation, you are coming back to the one stage prior, and then you are making modifications to the location of this solid. So in the next simulation, you may want this capacitor to be placed at a different location. So in that cases, you will treat such solids as the embedded solid. So in this simulation, I want this solid to be embedded solid. So I'm going to hide this. This is capacitor. So I'm going to hide this and consider all other parts as the bounding solid. So here I want to give the material as aluminum. Say OK. Now isolate only this capacitor and assign it as embedded solid here. Same. Yeah, aluminum is fine. Again, say OK. Show all parts. Now I want fluid cavity to be extracted automatically. So for that, what I'm going to do is just click on this button. The fluid cavity inside it is automatically extracted. I want material to be air here. So I'm going to select air as the material. Say OK. Now next, I'm going to click on the inlet here. This is going to be my inlet here. That is average velocity 1 meter per second and temperature 298 Kelvin, which is fine. Okay. Next, this is going to be my outlet section here. I'm going to assign this surface as the outlet, that is atmospheric outlet. Now, I'm going to hide this solid, this fluid cavity as well. And I want this capacitor surfaces to be at 350 Kelvin. So for that, I'm going to use this feature called phase and select this solid. And I'm going to give 350 Kelvin here as the temperature on the surfaces of the capacitor. Thermal condition, temperature 350 Kelvin. Okay. Next, I'm going to give this part as my heat source. So I'm going to select this part as my heat source, and I'm going to give some 500 watts as the total power for that part. Now with these boundary conditions, I want simulation to be performed. Now I'm going to simply click on this. Everything is fine. This resolution is also fine. If you want to see the grids, you can activate this. If you want to make finer grid, you can do that using this cursor. Now run the simulation. So the simulation will start and it gets completed in a minute. You can see the engineering quantities here, which are plotted as the time step is moving. So we have the average pressure here, we have the average velocity, then I have the average temperature at different locations, inlet, outlet, and boundary conditions which I have assigned. Yeah, the simulation is complete. So here you can see the temperature distribution now. I'm going to say view now. Yeah. So this is the pressure plot. If I want to check the velocity plot. So this is the velocity plot. The inlet velocity is 1.51 meter per second, which I have given as the inlet condition. So you can see the flow pattern, how it is entering and leaving the domain here, and how the flow distribution is. If you want to see the temperature counter, I'm going to switch it off. Open the cut section here, take cut section at mid. Okay, at this position. This is the velocity plot. If I want to change it to temperature, so this is my temperature distribution at this cut section. So imagine if you want to perform the simulation in using the traditional solver, how much time that takes and how much time the Inspire CFD is taking, and how quickly you are getting to know the temperature distribution and flow pattern inside this domain. So this is the greatest advantage of using the Inspire CFD. So now I'm going to change the pressure. So this is the pressure distribution. If I change it to velocity, this is my velocity distribution in the domain. If you want to see the minimum and maximum, it will be pointed. So likewise, you can perform number of simulation. Now say I want to perform one more simulation with capacitor in a different position. Now I'm going back to the geometry, hide this. I want this capacitor in a different position. So I can quickly modify that. Click on move tool here, click on the solid, drag it to any place wherever you want, and see how the temperature distribution is changing with change in the capacitor location. Say OK for this, show all parts, and directly click on the run button again. No need to modify any settings here. So I'm directly clicking on the run. So it quickly simulates and gives you the results for the modified design. Numerical convergence, you can see the convergence plot as the time step is moving. You can see the engineering quantities here. Yeah, the simulation is complete for this as well. So I'm going to click on this and view now. And now this is velocity. So you can see how the velocity, the flow pattern is for the new design. If you want to see the temperature distribution uh, at a cut section, yeah, I'm going to take a new cut section. I want it at this location. Yeah. Take the temperature. Okay. Yeah, so this is the temperature distribution at this point. So if you want, you can move it to the any location and you will understand the temperature distribution within the model. So this is the advantage of using the Inspire software at early stage, wherein it helps the designers to come up with the better designs. So again, you can save the simulation, go back to any stage in the geometry, make modifications to the location of these parts, and then again hit on the run section and check the flow distribution and temperature distribution. So this is where the Inspire CFD differentiates with the other traditional solvers. So here, yeah, uh, you can also include the rotating parts as well. If you are doing the fan analysis, you can treat that fan model as the rotating component and give the corresponding inputs and then hit on the run button to see how the flow distribution is, how the pressure distribution is inside your model. And here there are various materials which are inbuilt. If you want to create any additional materials for your model, you can also do that. In the material library, you have various pre-recorded materials, predefined materials. In the My Material, you can assign any number of materials that you want and use them for your analysis in the later stage. And there is also an option to include porous media, which creates the pressure differences. You can assign the porous media for those components as well. Yeah, yeah, I have covered almost everything that is under the fluid section here. So yeah, in the today's webinar, we have seen how Inspire CFD is helping design engineers for coming up with the better design at early stage. We did this fluid flow analysis, then the conjugate heat transfer analysis. We have seen how Inspire CFD software is helping design engineers with the innovative design. Yeah, so that's all from my side.